Okay, so before we start, I want to go back to a few slides that I have fixed. If you need help, I am in my office before this class. I am here after this class. I'm also available Monday, Wednesday, Friday, 10:50, AC2 1:15. Shoot me an email the day before to make sure I have class. So we are doing kinematics, so the study of motion in 1D. So for example, here you have a constant velocity. So the same speed and the same direction. So it means that every second, the same distance is covered. Here, the car is accelerating. Okay. So every second, it's moving farther and farther away. And the velocity is increasing at a constant rate. That rate is called the acceleration. So here the velocity is to the right, and because it's accelerating, acceleration is also to the right. Here you see the position, okay, for every unit of time. So it's slowing down, okay. So the velocity is still to the right because it's moving to the right. However, the acceleration is to the left. Okay, so when velocity, acceleration, they have opposite sign, that means it's slowing down. Okay, so just a review. I fixed my slide. I was missing one slide here, so it's back. By definition, the average velocity, so velocity is a vector, it's going to be the displacement over time. Okay, so that means you can have weird questions like if I run to my office and I go back to the same place, my velocity will be 0 because the displacement is 0, which doesn't really make sense in the real life, but that's the way it is. Velocity depends on the displacement. Displacement is the final position minus the initial position. Average speed is distance over time. Okay, so just reviewing. And then another slide. Okay, someone asked me a question here. So relative speed, and I think you have a question for the quiz, I'm not sure. But relative speed or relative velocity, it depends on your frame of reference. So if you are inside this car, okay, when they go toward each other, you add the speed because you're going to crash sooner. It will take less time for you to come together, right? So you add the speed. If you are not comfortable and you rather have equations, you have the equation here. So that means the velocity of this car relative to you, so you are in the red car, will be the velocity of the car relative to the ground, which is minus 35, minus the relative velocity of you relative to the ground. That will work also. Or you can do it with your guts. Okay, so we talk about that. Now, if you are going in the same direction, you need to, relative to the dot, of course, you need to add here, right? It will be 5 miles per hour. So we talk about that. And in that case, it will be 1 miles per hour. So what I forgot to show you last time is, so there is a YouTube channel also very good. It's called Flipping Physics. And he has also website where he has great GIF, right? And this is like a demo that you can do. You see, it's like a running sidewalk, and he's rolling the paper here. So this car is going at 42. You see, if the car is moving to 42 to the right, and the paper is moving at 42 to the left, from your perspective, it's not moving at all. Right? Does it make sense? Mm-hmm. So that will be like a demo you can do is if you have a toy car, moving at a constant speed, you hold this paper at a constant speed, and you can get it right that the car seems not to move. Now, if the car and the paper or the moving sidewalk are moving in the same direction, you see you add up the velocity. So it will be 42 plus 42 is 84. Okay? So that was about relative velocity. Okay. So check. What else? Okay, another slide that I had to fix here about acceleration. Did I pass? Maybe I passed it. Okay. Average acceleration is, by definition, the change in velocity over the change in time. Acceleration is a vector. The change in velocity is also a vector. So it's going to tell you how fast it's getting faster. So again, best example will be acceleration due to gravity. Okay, if I draw, it's going to speed up at down. So it's moving faster by 22 miles per hour. Every second, the speed increases by 22 miles per hour. So that's the meaning of an acceleration. It's a rate. Okay? And so I want to introduce the kinematics equation, and for that I want to do like simulation. So let's put your thinking hat and your participation voice. So this is the number line. Okay, position here could be negative, could be positive. Displacement will connect initial position to the final position. So let's say I'm gonna have him at position -8. So here, so that means when you start your stopwatch, the position on the number line is -8. And let's say the speed is 2. Our velocity is 2 meters per second. So it means it's moving to the right. Do you agree? Every second, it's covering 2 meters. Question for you. After 3 seconds, where do you think it's going to be? -2. So 3 is 6. 6 will be the displacement. But he was at 8. So -8 plus 6 is 2. Does that make sense? Okay. So let's see. He's moving at a constant speed. I have to stop at 3. Okay, about here. 3 seconds is at -2. So why I do that? Because sometimes you have tricky questions, right? Here. You see here? That position here, that's going to be your initial position, which means when you start your stopwatch, right? Now, the displacement, it's going to be 2 meters because every second 2 meters. So after 3 seconds, your displacement, okay, is going to be 6 meters, right? 3 times 2. Are you okay with that? So displacement, so it's going to be 6 meters, it's going to be there. So that will be your final position. Okay, so 6 meters is your displacement. But the location on the number line, okay, so delta x equals 6. So final position minus initial position, so it will be -8 equals 6. So final position minus -8, okay? So x will be -2. I don't need to do that. You can see that here. So I want you to distinguish between the initial position, okay, and the position on the number line here, which is, in that case, will be -2, but the displacement is 6. Okay, he is moving at a speed of 2 meters per second. So he is moving at a constant speed. Okay? Just make sure you understand that. That's based on the equation. So you start from here. After 2 seconds, you're going to be here. After 1 second, you're going to be here. After 1 second, you're going to be here. After another second, you're going to be here. After another second, you're going to be here. And so forth, and so on. Okay? So now, let's find the kinematics equation for the position. So x, the final position, equals what? What you're starting with. Very good. -8 plus what? 2 plus 2 plus 2 times t. Okay, so that's a kinematic equation. It's going to give me the position as a function of time. Okay, so the final position is what you start with plus your displacement. And then displacement is the speed times the time. So if I want to make it general, that means the final position equals initial plus the velocity times time. So that means this is a constant velocity. So that means there is no acceleration. And the velocity always stays the same regardless of the time. Okay? Now, let's take another example to make sure that everyone, yes. Now we have him at -5 and then 2. After 4 seconds. 3. Very good. Do you all agree with that? Yeah. The final position will be 3, right? So I have to do 4 seconds. Perfect. 3. Do you see that? Oh, I lost him. But in that case, the equation was the final position equals initial position was -5 plus 2 times t. Okay, so if t equals 4 seconds, final position is 3 on the number line. Okay? So now what's going to happen? Let's make it more complicated now. We could have some acceleration. So it means every second he will cover more and more distance. So let's say he's starting here. Initial position is -10. Maybe he had a velocity to begin with. 2. Okay, acceleration, I'm going to take, I don't know, -1. So is he moving faster or is slowing down? Slowing down. So after 3 seconds, after 3 seconds, no, I'm going to take 5 here. So after 3 seconds, how fast is going? 2. Okay, so he's slowing down. So let's see if it works. Whoa. Slowing down. And the velocity is, what does it say? 3. 2 seconds. 3 seconds. Oh, because it was 3 seconds. Thank you. Okay, so it's about 2. Okay? Okay, just to play with that. Now we can do the same thing with this app. So let's take an example. Initial velocity is 5. No acceleration. So it's moving at a constant speed, right? So what is the acceleration? 0. The velocity is 5. What about the position? It's increasing, right? So you're moving away from the origin. What's going to be the slope of position versus time? It's going to be the velocity. How do we know? Because look, a slope is rise over run. The rise is in meter, the run is in seconds. So rise over run, it's going to be the velocity. What's the meaning of the velocity? It means for every step in 1 second, you're going to go 5 meters further. Every step, 5 meters further. Okay, so at t equals 0, you're going to be here. 1 second later, you're going to be here. 1 second later, you're going to be here. 1 second later, you're going to be here. Okay, so it's just an introduction. I will get back to that. But now let's say I do initial position 0, initial velocity 0, and now I have an acceleration of 1. So what do you expect the acceleration to be? 1. Okay. What about the velocity? Is it going to stay the same or is it going to increase? Increase. So it means every second it should increase by 1. So it should be linear. But what about the position now? Because every second you're going to move further and further away. So it's not a line. It's a curve. It's a curve, right? Curving up. So it's called the parabola. So let's look. So it's accelerating. Okay, it's moving faster. You see the velocity here increases, 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 increases. Okay. So let's try to find the kinematics equation. At least 2. So for this one, the acceleration is 1. Okay. What about here? What's the slope? So look at the rise, meter per second. The run is in second. So what's the physical quantity meter per second per second? It's the acceleration. Okay, so every second the velocity increased by 1. Every second it's increased by 1. So the slope, if you have the slope, it's going to be 1. 1 meter per second per second. What's the equation? V equals what? Acceleration times the time, which is V equals t in that case. Do you see that? Just to give you a gut feeling, and then we'll go and look at those equations. So it's not a line. Do you agree with that? It's a quadratic equation. It's a parabola. So the equation will be x equals initial position is 0, initial velocity is 0. Here you have a 0.5. Here we're going to have the acceleration and t squared. So don't worry about that. We're going to look at that in details, but it's just to give you an idea that now it's not a line anymore. Okay? So just an introduction. Okay, so what is, that's it. Okay, so let me introduce you to the infamous kinematic equations. Okay, so first of all, you have all those physical quantities. The final velocity, so when you stop your stopwatch, initial velocity when you start your stopwatch, initial position, where is it you are on the number line when you start your stopwatch, the final position, where are you on the number line when you stop the stopwatch, the displacement, okay, it's a vector, how far did you go and which way, And acceleration depending on the force. If the force is on the left, acceleration is on the left, to the left. If the force is to the right, acceleration is to the right. And then it's a vector, and then you have t, which is a scalar, which is a time elapsed. Agreed? If you have an acceleration, these are going to be the kinematics equation, and we're going to use them today. But you see, the displacement, okay, will be initial speed times time plus 1/2, which is 0.5, times the acceleration times the time square. Or you can write the equation this way. It's the same equation. That will be final velocity equals initial velocity plus at. So this you already know. Acceleration is the change in velocity over time. You already know. This equation here is going to be very useful. Okay. Because it does not have what? What is it that the other three have and this one does not have? Time. Very good. Okay. So very useful when you do not have the time. Average velocity is the displacement over time, or initial velocity plus final velocity divided by 2, because it's increased at a constant rate. So typical motion with a constant acceleration, you're going to use those equations. So we're going to malax and massage them until you digest. But again, you need to use your textbook. It will make the medicine go down to the little spoon of sugar. Okay, so textbook is the little spoon of sugar. And then here, there is no acceleration. Okay, so the equations are very simple. Okay, that means the displacement is just velocity times time. Okay, so this comes from the book Johnson and Cutnell. Okay, and so the first thing you do with kinematics problem, you decide which way is plus, which way is minus. So usually right is plus, minus is left. Kinematics 1D, you have the number line, okay? And you're going to make a sketch always. And you put everything you know on that sketch. So here it says, here, when you start your stopwatch, the velocity is 6. When you stop the stopwatch, velocity is v, and the acceleration is 2, which means after 1 second, how fast is it going? But it had 6 to begin with. 8. And then 1 second later, it's going to be 10, and so forth, and so on, right? And you have your equations here, so that will be the displacement. You can put a delta there. Okay, so I show you one way to do it. So step by step. Okay, so you can make a table here. So that will be your displacement. So I can put a displacement here. Okay, so what do we know? Initial velocity is 6. Okay, 6. Acceleration is 2. Okay, 2. Time elapsed is 8. So I put 8. And then you want to make sure to have 3 numbers. 3 out of 5. You only need 3. Once you have 3, you can solve everything. If you have only 2, that means you are missing something. Then you put your question mark here. And here you say IDC. I don't care. IDT stands for I don't care. Okay, and then you look at your equations. And you want an equation with delta x, a, and then initial velocity and time. So you can help each other if you want. So you have the choice between 1 and 2 and 3. Maybe you are missing velocity. Average velocity is delta x over time. Initial plus final. Divide by 2. So which equation do you think we can use? Equation 2? Okay, so if you use equation 2, it's going to give you the final velocity, right? But they are asked, well, that will be right, except that they are asking for the displacement. So if you do that, if you use number 2, then you will have to plug in number 3 to get the displacement. So which equation can we use? The first one, right? Either you use 2 and then 4, or you use the first one. Okay, so delta x equals initial velocity 6, so 6 times time elapsed is 8 plus, instead of putting a 1/2, you're going to put a 0.5 because it's easier with the TI, times acceleration times the time square. So that way, with the TI, you do that in one shot, right? So 6 times 8 plus, you do it this way, 0.5, and then a 2 here, and an 8 square. Okay, so you take shortcut. And what you get, 112, yes. Meters, you want to make sure to have the right unit. So meters has to be meters all the way. So the answer is, so the displacement here is 112 meters. We could find the final velocity. Can you find the final velocity now? So final velocity will be what? 22. 22? So initial velocity is 6 plus 8 times 2. Is that right? So you can find so every second it's accelerating by 2 until 8. Right? So 16 is the increase. You see, this is your delta V, right? So second times the rate plus whatever you begin with. That's your delta V here. Okay? And you do have, like, if you didn't get the book yet, which I recommend, in Canvas, on Canvas you have link to free textbook, algebra based, and you even have a YouTube channel that will solve the problems that goes with the free textbook. So you have a lot of support. So let's apply the same methodology here. So you know how they do that? They have like a slingshot, right? Like a catapult. No, not a catapult. Like a slingshot. Yeah. Slingshot? Yes. Not a catapult, right? Catapult will be very bad. So you see there is a huge acceleration. This is huge here. Okay, because you know how do you know if it's huge or not? You compare to the acceleration due to gravity, which is 10 meters per second, which is 1 g. So this is about 3 g. So if you are inside the airplane, you're going to feel 3 times your weight crushing you. Stomach. You have to be a trained pilot, right? Cannot go over 10 g. Because the blood doesn't go to your brain. And then you pass out. Which could be very bad, of course. Okay, so initial velocity is 0. final velocity is 62. Acceleration is 31. This is IDC. Displacement here, question mark. Okay? Okay. If I want to make my life easier, which equation I could use? The last one. Do you all agree? Because there is no time. And then physics stops and algebra takes over. So if it's hard, you blame algebra. So 0 square plus 2 times 31 over delta x. And delta x is the unknown. So you are solving for delta x, okay? So do it. So 62 squared equals 2 times 31 is 62, delta x. If it's confusing, you can say 62 delta x equals 62 squared, and you divide both sides. So the answer is 62. Right? Do you all agree? And if you don't agree, go back to algebra or see me after. So you divide both sides by 62. Okay? So the displacement here is 62 meters. You could find the time if you want. Let's find the time. How long does it take? Okay, so final velocity is 62. Initial velocity is 0 plus 31 times t. So the time elapsed is 2 seconds. So in 2 seconds, 3G, your stomach is not going to be very happy. You know the stomach, you are in biology, you know, it's like a sensor. It's a acceleration sensor, right? So some people, they feel sick, car sick, right? Because they have a very good sensor. So the displacement is proportional to the elapsed time only when you have a constant no, so if you have an acceleration, remember you have a parabola. So if you have an acceleration, the displacement, you have a t squared. If there is no acceleration, that term goes away, and the displacement will be just proportional to the velocity, right? Or initial velocity or time. Okay, because initial velocity is a given, so it will be proportional to the time. Okay, we're going to see that when we're going to go to graphing analysis. So if it's a constant velocity, then the displacement is proportional to the elapsed time. If it's proportional to the elapsed time squared, it's a parabola. If it's a parabola, that means there is an acceleration. So get like together, not together, but help each other, like find someone next to you. So this one is a tiny bit tricky, but it comes from the textbook. By the way, I have also a link, I think I put that in my announcement, to a YouTube channel where the professor goes over those slides as well. And he also have demos, right? It's also based on the same textbook. So here it's a little bit tricky because look, this is meters. Here you have the displacement in kilometers. Can you keep kilometers? No, so I have to convert that to meters. In addition to that, they try to trick you because it says the spacecraft slowing down. It's slowing down with an acceleration, which is a vector, and the magnitude is 10. So a vector has a magnitude, a unit, and a direction. So if the spacecraft is moving to the right, but it's slowing down, the acceleration will be negative, right? So if it's slowing down, acceleration, velocity have opposite direction. So make sure to have a drawing. Try to draw the situation, make a sketch, and then you can help each other discuss, which equation to use, and then you can blame the algebra. So you have a spaceship, a spacecraft here, and when you start your stopwatch, it was already moving. So I can put a 0 there, right? It doesn't say initial position, so let's suppose it's at 0. That's your stopwatch here. You start your stopwatch. And then it's slowing down. And maybe at some point it's going to stop. So much slowing down. Okay, and here that will be the final position. And acceleration is -10. Everything is in the drawing. All the physics here is in drawing. And displacement, you connect your starting point to the final point, and it's 2, 2, 1, 5, 1, 2, 3. So displacement 215 -10. Okay, what is the final velocity? Okay, 3250 IDC. And you look at your equation, delta x equals nya 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 t square, and you have what acceleration is final minus initial over time. And then you have v square equals initial square plus 2 times delta x. And then you have average is delta x over time. Okay, and physics stops. Now math takes over. So which equation I can use? Exactly, because there is no time here. Okay, so I'm going to use this one. Do you all agree? Mm-hmm. So I'm going to plug it in. So it's going to be 3, 2, 5. No. V square. That's what I'm looking for. V square equals 3250 square plus 2 times. Acceleration here, you have to be very careful to have a -10. Because if you don't have your -10, you're going to add instead of subtracting. Displacement 215123. Okay, go. Algebra. Okay? With your TI. So do it so. 3,250. Don't wait for me, okay? Don't stare. Look, if you have a TI, it's very nicely done. Minus 10, and then 215,123. Close the parentheses. Boom. And then you have to take the square root, right? And you take the square root. How many roots? 2. So let's take the square root. So you do second square, that will be the square root, and then you call back here the answer. So you go second minus, and you get plus or minus 2502. Okay? And then you can think about significant figures or not. I do not care much, but plus or minus. So you have two solutions. Let's think why you have two solutions. So it's in space. So to be able to slow down those spaceship, they have like retro rockets. Okay, so they're gonna fire this way. So there is a force pushing in the opposite direction, right? So it's gonna be pushed this way, even though it's moving that way. Do you understand? So what's gonna happen to it? It's gonna slow down. Eventually, it's slowing down so much that it's gonna stop, but you keep pushing. So what's gonna happen to it? Very good, it's gonna reverse. It can happen with a spacecraft. Of course, with a car, when you slow down, you're gonna stop. You didn't see a car moving back. That would be very weird. But with a spacecraft, you can do it, right? So you keep your rocket on, and now you're gonna be in exactly opposite direction with the same speed, but opposite velocity. So it will be the same speed here. Then you can keep going there, right, at the same acceleration. So the rate at which you are burning your fuel. It's a little bit more complicated than that because of course you are losing fuel at the same time. But you can arrange to have the same acceleration. So finally you're gonna have the same velocity here. Isn't that cool? Sort of. Mm-hmm. It's like you do some exercise at the gym and you attach someone with a string, not an elastic, but a string, and that person starts to run and you pull always with the same force, right? At some point, that person is going to stop and you're going to bring that person towards you. Kind of. I don't know how to do that experiment. Okay, so they show you here. You see it's moving to the right, but it has a retro rocket here, so it's going to slow down. So slowing down, stop, reverse. So for those two locations, you're going to have the same speed, but not in the same direction, and the displacement will be the same. Okay? So it says 2.8. Let's see if I have a 2.8 somewhere. Okay, we can try to do that. That's from the textbook, but the textbook recommended by the department, if you have this one, it doesn't matter. Let's do this one. So here what is interesting is you don't have the sketch, right? So you have to do a sketch. So try to do it. So it's like reading comprehension. That's what it is. Reading comprehension. Why is it Iowa? I don't know. Maybe the authors are from Iowa. I don't know what is in Iowa. So you have the city limit here. Gonna put that 0. So this is x equals 0. Read and translate. Do it. Okay, so here, when you start your stopwatch, is here. So you have to translate what you read in a sketch, right? And what else do we know? We always put the acceleration on top here. So that means the velocity will increase by 4 meters per second every second. So every second you go 4 meters per second faster. Okay, so this is when you start your stopwatch. Stopwatch here. So at t equals 2 seconds. The final position. It's a little bit tricky. Because we're gonna use so the equation is delta x, the displacement equals initial velocity times time plus 0.5 a acceleration times t squared, right? Okay, so try to do it. Don't stare, nothing will pop up. So what you want, let's find first the displacement delta x here. So that equation of kinematics here, you have displacement, right? Don't forget, it's a delta. So initial velocity, when t equals 0, acceleration, the time elapsed. Okay, so plugging in, like in the song, plugging in. So you can talk to each other if you want. You plugging in. What's the initial velocity? 15, right? Yeah. Times time elapsed is 2 plus 0.5, acceleration is 4. Time square is 2 square. Okay? And you get what? 38. 38. 38. So just to show you how you work with the TI, times 2 plus you do a 0.5 times acceleration times 2 square, 38. Do you agree? But that's the displacement. And what do they want? They want the displacement or the position? from the city limit. The position, this is 38 meters. So you went from here to there. But for strange reason, you decided that your initial position, the origin is here. So where are you on the number line? 43. Do you agree? Okay, if it's confusing, you go back to the definition. What's the definition of a displacement? It's the final position minus initial, which is 5, equals 38. So the final position is 43 meters. Okay, so that position on the number line is 43 meters. But the displacement, remember, you connect when you start your stopwatch, when you stop your stopwatch. So that will be the position, the displacement. Okay? Like with the walking man. You can do the walking man on your own. It's gone. You walked away. But I know it's on Canvas. You have the app on Canvas, so you can play with it. Okay, so let's answer question B. So now, where is the motorcyclist when the final speed is 25 meters per second? Okay, so now we know the final velocity is 25. Mm-hmm. The initial velocity is still 15. The acceleration is 4. And you want to find the displacement delta x. So you have your kinematic equations. Look at them. Right, so the first one is delta x equals initial velocity times time plus 0.580 square. The other one is final velocity equals initial velocity plus 80. And then you have v square equals initial square plus 2 times acceleration and delta x. So which one do you think is good to use? Yes, the last one. Okay, because there is no time. Is that clear? So then you plug in, but again, you are finding delta x. You are finding delta x, right? Okay, so 25 square equals 15 square plus 2 times 4 times delta x. And you are solving for delta x. So minus 15 square. Did you get 50? So you do 25 square, enter, minus 15 square, enter, and you divide by 8 to isolate the unknown, right? It's a little bit, this problem is a little bit more challenging. So what you get? 50. So now the displacement is 50. So it means from here, okay, you went to 50. And the motorcycle has a speed of 25. So displacement is 50, but you were 5 meters away when you start your stopwatch. So it's going to be 55. Right? So x minus initial equals 50. So x minus 5 equals 50. So final equals 55. So this one is a little bit tricky. Not that much, a little bit. I don't know what it is. Okay, any question? Okay, so the app. I'll do that later. Okay, now easy. Let's practice. Let's do let's do number 2. So these are easy. You have the solutions in Dropbox. Bon. Number 2, did I say? Okay, let's do number 2. Okay, you can always make a drawing. Initial velocity here. You can make your car here. Initial velocity is 30 meters per second. So that's the initial. That's when you start your stopwatch. And then what's going on? It's going to slow down. So you have to make your acceleration this way. So every second, it decreases by 3 meters per second. Well, that's easy, right? So it's slowing down. So what's going to be the velocity? Huh? 21? Yes, you're right, 21. So you can use V equals initial plus AT. So final velocity equals initial 30 plus minus 3 times 3. Okay, or it's easy, you see it decreases by 3 every second. So after 3 seconds, you decrease by 9. So it's 30 minus 9, which is 21. Do you agree? Okay, and easy also. What's the displacement? So 9, so which equation did you use? The first one? So we can use the first or the last. So delta x equals initial velocity times time plus 0.5 at squared. So delta x equals initial velocity is 30 times 3 plus 0.5. And here you have to be careful to put a negative 3 and 3 squared. So what you get? Huh? 76.5, yes. So 30 times 3 plus 0.5, and then you have a minus 3 here, and then you have a 3 square. So I'll show you how to do it quick. So yes, right, 76.5 meters. Question? So that means it's the displacement, okay? So initial position to the final position. 76.5 meters. Okay? Just the equation sheet here is gone. But I wanted to show you the equation sheet. I don't know if it's there. I have a lot of equation sheets, so I don't know which one is the right one. It's not the right one. Okay, so that's the equation sheet. I think you have that equation sheet, but you have to get used to them, because you see here, instead of using delta x, they are using delta s. Why is that? Because you could be moving along the x-axis, or you could be moving along the y-axis. So s could be x, or it could be y. So s could be x, so it could be delta x plus v0t plus 1/2 at squared. So you see here, you have your equation. So this one means average the speed. Okay, so the average velocity is just initial plus final divided by 2. So get used to it and don't wait for the test to say, oh, okay, I'm confused. You are not using the same notation. So I'm telling you that I am not using the same notation as the equation sheet. So if you have questions about the equation sheet, just ask. Okay, let's do, which one do you want to do? Let's do the last one to see if you are paying attention to what I'm saying. So if you go back to my slide, you see, for the average velocity, when you have a constant acceleration, the average velocity is displacement over time, or it could be also initial plus final divided by 2. Okay, so you have two equations for the average velocity. And I think I already talked about that. It's because you see the velocity here and you have the time. If the velocity increases at a constant rate, does that make sense to you? So it means it starts with the initial here and final there. Does that make sense to you that the average will be just the midpoint? Okay, so the average will be the midpoint, the middle. So it will be initial plus final divided by 2. Because it takes as much time here than it takes there. Do you understand? So if the first grade in physics is 0, and then you increase by the same number, right? So the rate is the same. Second grade is 10, 20, and then 30. What's going to be your average? About 15, just in the middle, because the rate is constant, and you fail. Not that I want you to get that, of course. But of course. Okay. So how can we find the average velocity? Okay, so it's the initial plus the final divided by 2. Okay, because it's the midpoint. The midpoint, when you want to find the midpoint in geometry, you take the initial, the final, and you divide by 2. Convince yourself, right? If you do 2 and 4 and 6 and 8 and 10, right? It increased by 2. How much is 2 plus 10? 12 divided by 2, so it's 6. Okay?
What's the answer for that? 3.
So the answer is 6. 6. Okay. Let's do those one just to make sure you understand. So look at your equation. So have your equation next to you. So what are the equation? You have the first one is displacement equals initial velocity times time plus 0.5 times acceleration times t squared. Agree? Or you can say the final position is initial position, what you begin with, plus v0t. Okay, so that will be if you have no acceleration. But because you have an acceleration, you're going to be further away on the number line. And the other equation is final velocity equals initial, what you begin with, plus the rate times the time. So now it says initial velocity is 30. Acceleration is 10. Initial position is 0. What's going to be the equation of motion? So x as a function of time. So you use this, right? So plug it in. So we are connecting to algebra, right? When you have algebra, you have f of x equals nya, 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 right? So this is called y sometimes, or f of x, and this is called x. But in physics, you know what they say, what's in a name, right? So I don't have to call that y. So in physics, they decided we're going to call that x, because that's a position. And instead of x, you're going to have the time. Okay, so we're going to have a function like this, like 3t plus 5, for example, and that will be my position. So just a parenthesis for those who are confused, where is x? X is my y, and t is my x, because Shakespeare said, what's in a name? So anyway, can you do it? Take that equation here. Don't stare. I see people staring. Staring doesn't help. Do it. Do. Step by step. X equals, do we have the initial position? 0. So I'm going to put a 0 plus, do we have an initial velocity? So 30 times t. Okay, it's an equation of time. Okay, plus 0.5. What's going to be the acceleration? 10 t squared. So it's like in math, it's called a quadratic equation, but the x that you usually use in math, it's going to be the time, and the y that you usually use in math, it's going to be the x. Okay? You connect the dots. So let's make it more aesthetic here. So it's going to be 30t. 0.5 times 10 is 5, so 5t squared. It's a function of time. Do you understand? You can even put, like you did in math, right? The time and the position on the number line. So at t equals 0, where is the object? When you substitute t by 0, 0, very good. When t equals 1, Substitute t by 1. What do you get? Very good. 35. When t equals 2. 20. How much? So 80. 80, thank you. And t equals 3. So 3 times 3 is 9. 9 times 5, 45. 45 plus, thank you. and so forth and so on. Okay? So what does it mean? It means that at t equals 0, it's at the origin. At t equals 1, it's at 35. At t equals 2, it's not at 70, it's at 80. And at t equals 3 is over there. So this is acceleration because every second you move farther and farther and farther away. Got that? Now, if I do like you do in math with a spreadsheet, you can do that. Will be a good practice. Time here. X is here. X, t equals 0 is going to be here. T equals 1 is going to be at 35. T equals 2 is going to be farther up and farther up. And you're going to get a nice parabola. Okay? So we are trying to massage those kinematic equations. What about V? Can you do V? So V as a function of time. Don't stare, help each other. So V, use the kinematic equation. What's the initial velocity? 30, very good, plus acceleration is 10 times t. Let's connect to algebra. T, velocity. At t equals 0, what's the velocity if you plug? Very good. At t equals 1, it's going to be 40. At t equals 2, it's going to be 50. At t equals 3, it's going to be 60. So for each run of 1, I hate to hear my voice. Stop that. I hate my voice. I cannot hear my voice when I speak, but I can hear my voice when I really don't like my voice. I have a very high speech. That's why you cannot fall asleep in my class, okay? My voice is so annoying. So velocity as a function of time. So what do we get? So what kind? Is it a parabola or is it a line? It's a line because every run of 1, you rise by 10, you rise by 10, you rise by 10. So this is 30. Every step of 1, you increase by 10. And the slope will be the acceleration. Okay? So that way it's easier to understand. Question? Okay, so now why don't you really talk to each other to find what's the number 7? So we have equation delta x equals initial velocity plus 0.5 a t squared. It's good for the MCAT too because we are reviewing math. Displacement. So this is the kinematic equation. X equals initial position plus V0t plus 0.5 at squared, right? That's what you want to use. So this is really algebra. So we have x, that's the kinematic equation. And now we have 5 plus 10t oh no, here is a 2, right? So it's a little bit of algebra. So initial position is going to be 5, right? So 5. What about the initial velocity? 10. A little bit tricky. Half of whatever is 2. It's going to be 4. Acceleration is 4, right? So if you are confused, you see here, it's going to be 0.5. Half of a is 2. So a equals 2 divided by 0.5, it's going to be 4. Or half of question mark is 2. That question mark has to be 4. So acceleration is 4. Okay, so on the number line, you start your stopwatch here, and then you're going to move faster and faster and faster. And that will be your position, initial position, when you start your stopwatch. Okay? Let's do number 8. So x equals initial velocity plus initial t plus, and it's good because we are reviewing math at the same time. So when you see a t squared, the coefficient is the invisible 1. So what's the initial velocity? No. Because you see no, you're right. I was thinking initial position. You're right. So it's 10. Initial velocity is 10. Very good. And what about the position? 0. Okay. What about the acceleration? 2. Very good. Okay. What about x equals 10t squared? What's the initial position in that case? 0. What's the initial velocity? Velocity. 0, because velocity goes with t. T squared, you have the acceleration. So half of what is 10? Half of what is 10? 20. Acceleration is 20. Are you with me? So because the equation is x sub 0 v0 t. So the velocity goes with t, and the acceleration, or half of the acceleration, goes with t squared. So in front of the t squared, I have half of the acceleration. Okay? If it's not clear, let me know. Number 10. So we have to do that in 2 steps. Steps. So what's the initial position? 5. What's the initial velocity? 10. What's the acceleration? 20. Very good. Do you all agree that it's 20? Because that here is half of the acceleration, or 1/2. Okay, so now, how can I find the final velocity? Yes. So what's the initial velocity? 10 plus, what's the acceleration? 20 times 5. Yes. Is, yes. So V equals dx over dt. So I see where you are going, but that's for people who took calculus. If you take the derivative of this, you're going to get that equation here. Right? You're right. So for those who took calculus, if you have x equals initial position plus velocity times time plus 1/2 at squared, and if you take the derivative, so dx over dt, okay, derivative, that's going to be 0. Derivative, that's going to be initial velocity, and you're going to get at. You're right. But that's for calculus based. But that's, you're right, that's how we get that parabola. Okay. What about this one? Number 11. So here, what's the initial velocity? 10. What's the acceleration? 2. What's the final velocity when t equals 100 seconds? So v equals initial 10 plus 2 times 100. So that will be 210. And what's the equation? Magic equation? Think of your grade. How can we find the average velocity? Initial plus final divided by 2. So initial was 10 plus final by 2. Yes. 110, is that right?
Yes.
Okay. So again, textbook, you can practice. Okay, let's do number 5. All those, you have tutorials in my Dropbox, except because I keep changing my slides. Not changing, but sometimes the numbers might be off, because I like to update stuff. So what is the acceleration? So you're going to do a question mark. So with those kind of problems, you can identify the physical quantities, right? So what is the acceleration means a question mark. Blah, 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 blah. What's going to be the 360 meters? Huh? So it's going to be delta x, right? The displacement. 5 seconds will be the time elapsed. And then it says something interesting. Starting from rest. So initial velocity equals 0. Accelerating uniformly. That means that the acceleration is constant and I can use the kinematic equation. If it's not the case, you can't. Okay, so look at your equation. I don't know how to draw a rocket. So it's gonna move faster. So you have the displacement and the time elapsed, right? So help each other. So time elapsed is 5 seconds. Delta x is 360 meters. Initial velocity is 0. Oh, and you want the acceleration. Okay, so we can do it in 2 steps. Let's see. So you can do delta x. Oh, yeah, we can use the first one, right? Okay, so delta x equals initial velocity times time plus 1/2 at squared. So delta x is what? 360 equals initial velocity is 0. Okay, so that term is not there. Acceleration and the time square is 5 square. Is that right? So I'm glad initial velocity is 0 because otherwise we have a quadratic equation to solve. So you can rearrange. So what is the acceleration? Let's see. Okay, you're right. 28.8. 28.8 meter per second. Right? And if you want to be annoying with a significant figure, you want only one. So in that case, that will be 30 meter per second. Okay? And so you see, you can practice. Is it open? Yeah. Okay. So for next, oh, this is a little bit more challenging. So if you want to be ahead, you can try 51, 52, and then we go again to graphical analysis.